is already? Good. Well, thank you very much for the opportunity to be again in Newton Institute. I was here about 10, 11 years ago. I'm not sure it's the best one, but it's certainly one of the best. And especially can find the best people, that is true. Okay, now after this very interesting mathematical talk, I will give you more mathematical physics talk with very challenging open mathematical problems, you will see. And in fact, I will start. So my talk, in fact, was, for a long time I had this idea, but I only started after being somehow encouraged by Vladislav Puknachov that visited me last June in Lisbon. I was discussing, and he's a specialist in fluid dynamics. And I'm not really sure about if the mathematical model I'm going to speak today is the good one for the kind of fluids that I dare to call them thick fluids. If you Google thick fluids, maybe now when I put something there will start to appear, but it's a name that I never found before. They are thickening, shear thickening fluids. And thick fluid is a kind of limit case that we will see. Okay? So in fact, it appears as a symptotic model for a certain parameter, a power, when it goes to infinity. And I will take the case, the model case, where in the limit you see basically you have these kind of rheological graphs that represent shear rate against shear stress. So you put some stress in some fluid, you have some deformation, and the velocity of deformation has this kind of behavior. The Newtonian fluid, leading to all known Navier-Stokes equations, is basically a linear relationship, okay? Newtonian, corresponding to a power equal to. And if you have in the power type law, so a relation between the shear rate and the shear stress as a power, if P is smaller than 2, it's called so-called pseudoplastic fluids. For P larger than 2 is the so-called dilatant fluids. In a certain sense, what I'm going to do is let this P goes to plus infinity. And you see, basically what I shall get is some kind of graphic of this type. Okay? Of course, the fluid is more complex, and these kinds of fluids, and in fact, this kind, when these dilatant, they are also called the shear thickening fluids. And in fact, sometimes it's not just one power. There are several powers. They are complicated. And you can see, I'll show in a minute in next slide. I was motivated then searching in literature what's going on. And in fact, it's been, last decade at least, an increased interest in rheology about this kind of fluids with experiments, basically also for military reasons, because this is for the ballistic experiments, these coats, this armory that prevent policemen or soldiers to be eaten by bullets. And in fact, the effect is a kind of the strong stress somehow solidifies the fluid. And kind of the experimental plot between shear rate and viscosity may present these vertical lines, that's a certain critical shear rate values. And in fact, there is a featured article in Physics Today in October 2009 when this is described by these two authors. And in fact, I was discussing with my colleagues in chemical department in Lisbon, my university, and asked for some references. They had a little bit difficulty to understand my mathematical way of thinking. It was a bit difficult to understand their chemical way of thinking, but they gave me some interesting reference about these composite materials. And in fact, then I start to look a little bit, and then we get this, notations. And in my talk, I will treat basically two parts. The first part is just, from a mathematical point of view, go to P plus infinity, and to get the vertical line as an obstacle or for the absolute value of the destroying velocity. So U is, and you should remind U is the velocity field, so is in 2 or 3D. I write here just to, so this belongs to Rn is equal to 2 or 3 in physical cases. And D is the symmetric part of the gradient. Okay, and the constraint will be of this type, with 1 in this limit case when p goes to infinity, but I can treat more general case where psi is a positive function depending on x and t with some regularity. In fact, what should be interesting and maybe for further work is to consider that this psi may depend on other internal variants of the fluid, like the pressure, the temperature, the composition, whatever. Because in fact, it's not clear that this vertical line stays always at the same critical value. In fact, this is not the first class, so first type of fluids with vertical slopes. It is well known that the Bingham fluid, which is a kind of rigid component, so the flow only starts after the stress reach a certain positive threshold. So you need to put some, it's a different kind of fluid, okay? And the Bingham type fluids have been well studied, and in fact, Duvaulions used Bretian inequalities, and you will see that this kind of monotone graphs will lead to this kind of Bretian inequality. My approach is related to Bretian inequality indeed. But before I go into mathematical details, let me just show you a very nice, motivating picture. It's only 2 minutes. Not me. No. They are Spanish guys. Go back and forth. Okay, so I hope you've enjoyed, because I think this is a very nice motivation. What? Now, I don't know what is material. I just found this in the internet, and in fact, I can give you the reference if you like, but I don't know exactly. I just found it to Well, no, I think I'm not sure if in fact these thick fluids are what we have seen. Okay, maybe the fluid is more complicated because we have seen the law is not exactly this one. Nevertheless, I think they have some relationship. Which one I don't know exactly what is, but they should be related somehow. So let's go now to a little bit to mathematical physics, to mathematical formulation of this problem. And so I will start with a dilatant incompressible fluid. And I will use as the constitutive law between the shear, I mean the rate of deformation, the U, and the stress tensor S, a kind of law, power type with two components that was proposed actually in '67 by Galizianskaya. In fact, she proposed this with Q equal 2 In fact, at that time, she was looking for more complicated laws that could lead to the uniqueness of solution of the problem. And in fact, if you formulate what basically corresponds to Navier-Stokes equations, if P equal Q equal to 2, is just Navier-Stokes equation. And in fact, you have the convective term there, the pressure pi, some external force F, incompressibility condition, the divergence of U is equal to 0, and to simplify initial data and the homogeneous data on the board. And in fact, there is still interesting issues, as you know. This is one of the millennium problems. And by the way, the millennium problem, just a small remark, has been formulated by Leray in 1934. If you go to read his original paper, it's there, the open problem. Of course, it was renewed in 2000, as you know, as one of the institutes. Okay, but this is out of this talk. But in fact, what was known in the 70s, or even the end of the 60s, Lejeska and Lyons, in the end of the 60s, they were able to show that for P larger than this critical value, which is 2 in dimension 2, in fact, it's not n, it's d. For dimension 2 is just 2, but for dimension 3 is larger than 2, is 5 halves. That in fact, this is a well-posed problem. There is existence or uniqueness of solution. And since you are interested in letting P go to plus infinity, you can let P be larger than this critical value. In fact, very recently, a few years ago, 3 years ago, there is an interesting paper in Ollie de Pisa that this paper has been, the existence has been settled up to 6/5 in dimension 3, in three-dimensional case, and below this value, this is a critical issue, there is no weak solutions, it's known. Not known weak solutions. In fact, there are measure value solutions that are quite strange. But in any case, what concerns us is the opposite, not for small p's, but for large p. So we start with a dilatant fluid, which has existence and uniqueness of a classical variational solution. And in fact, I can take the viscosity as a parameter that I can let be 0 in some cases, because it can be compensated by this component. So notations now I think are clear, and for this problem, we don't need to work much to look into literature, to introduce the functional spaces, which are the standard closure of the solenoidal smooth vector fields. And I call it H, the closure in L2, V, the closure in W and R, where R is the normal Sobolev space with the D components. But these are solenoidal vector fields because we deal with incompressible fluids. And we can start by a proposition that is now. You can go to the literature and to see that in fact for every force in L2, every initial condition also in L2, level 0, there is a unique weak solution in these spaces. And in fact, in this case, the time derivative is a distribution, but can have this variational formulation almost every t. For almost every time, we have standard variational formulation. And since we have put p larger than, so the assumptions we have, in fact, are, well, I wrote before. So I take the assumption that p is larger or equal than p plus 2, so I don't have problem with uniqueness. And what is important is that we have the a priori estimates with respect to this parameter p, because I want to make now p goes to infinity. And the first estimate does not cost you anything, is standard, just take as test function basically u, which is okay, integrate in space and time, in time, and you get automatically the basic energy estimate, and this constant does not depend on p. I shall need another estimate to estimate the time derivative. There already something is required for the initial condition. If the force in L2 is enough, because I just can take formally the test function, the time derivative of the velocity, u is velocity, integrate, and you get the kind of energy estimate for the velocity. But you need to get rid, well, this convective term is not too bad because you can absorb it by the q part. I mean, here I must take mu positive, so I can take the mu part in this term, and that part is a bit more delicate because I need, in fact, a condition on, if I want an estimate which is independent of p, I need to take the initial condition now already in this convex set. I'm going to take the initial condition which has the velocity of deformation in absolute value, small or equal than 1, almost everywhere. Because when I integrate, when I take here the time derivative, this SP has a potential, basically. Take the primitive, and on the right-hand side, the initial condition is controlled because it does not depend on P, because of this, okay? But that's what I want. I don't want to work with very weird solutions initially, so I take this initial condition, and I get this a priori estimate, which is independent of P. And now is a matter of making the P goes to, take subsequence and go what's happening, which is more or less standard. And in the limit, I can state this theorem. And this theorem states that for, now we can fix the R, since P is going to infinity, fix arbitrary large R. And the solutions, since they are a priori bound in those spaces, they, the time derivative converge weakly in L2. And as a consequence, and by compactness, the UP converge strongly in values in L2 and weakly in R with values in VR. And then we go to the limit and we get not an equation, but you get an inequality, which is a variation equality of the Duvaux type. But we have now that the solution itself, V, I call it V, sorry. The limit velocity is called V, should lie in the convex set K1. I will write here to remind you. This Q1 is the, so it's VR. VR is basically the solenoidal field in W1 such that so the solution for almost every T should be in K1. It is continuous in L2 values, so the initial condition is satisfied without any difficulty. And you get a variation equality. I put it here. So to remind you the formulation when I go ahead, I write it here for this means the product of matrices, of course. This is the tensor product of the two velocities.
What is Q there? What is Q?
Okay, I recall this law. My initial law was something of this type. So I have a power in P plus a viscosity mu with a power in Q. So my Q is any value between 1 and infinity, while my P is this value that is going to tend to infinity. Okay? Now I need to finish my variation equality. For any test function in K1. And this is almost everywhere. And of course, we have that the initial condition is given in K1. Okay, and I claim that if mu is positive, we have uniqueness of solution because it is bounded. So the convective term is controlled easily, and you can apply Grunwald basically.
How do you get inequality? Is it because...
Okay, I came by monotonicity. This is a monitor vector field. Okay, so S of D, if U, or yeah, so W minus U is greater or equal to S. Excuse me, this is SW or SV. Okay, I want to put it in this form. Doesn't matter. Doesn't matter. Okay, you have V, S, T, W. Let me put D here. So this is V, this is W, this is V, this is W. Okay? This is a monotone vector field. So when I integrate, I will do it, in the proof you'll see it. But this is the standard way to get variation equality for, okay? So this is my first theorem, and I think you almost understood how I can obtain it. I want to make two remarks before proceed. The first one is, if we take Q equal 2, we have the Navier-Stokes equations in this domain, assuming that we have a way to define smoothly this domain, this is open, okay? But of course, what formally we get for this solution is a splitting of our region into two parts, where the threshold is not attained, and we have the fluid flow equation, and when the threshold is attained, and there, well, something happens, and in between we can tell the boundary of this set as the free boundary of our domain. And everything is open, at my knowledge, in the vector case. We can think about a scalar case, which corresponds to a unidirectional flow. If you take the velocity field, U, I mean, in 3 dimensions, say the function of x and y, so this is the x component, S and Z, and you just take a flow in one direction, this problem reduced to a scalar one. And the constraint is just the gradient. And that, at least in the stationary case, it's the well-known elastoplastic torsion problem. For the time-dependent problems, it's been considered, I will come back to the reference later at the end of my talk, by Lisa Sanch. And in case of mu0, and the scalar case, this is the module for the sand pile growth. And also, that's being studied by Prigozhin, and there's Ronson, Evans, and others. And but what is interesting exactly that in this model now, since we have a very strong control on the gradient actually, on the d of v, we can let mu goes to 0, and we get existence. Okay, the problem of uniqueness is more delicate, but you can get uniqueness for the. And can get existence, sorry, for the non-viscous problem, which corresponds to Euler equations in the flow region, or in more standard flow region. But of course, the uniqueness in this case, I don't know how to prove it. Okay, so this is the first theorem, and try to convince the theorem is correct. I give you some ideas for the proof. Okay. One main point is, of course, to deal with, okay, we have already a priori estimates, I explained that, is to check that this limit function actually satisfies the constraint. This is the first most important point. But since we have, remember this a priori estimate is the, well, put here the p and 1, and you see that we have the power p of the LP norm of d of up is controlled by a constant independent of p. I mean, this means basically what is written here with this C0 is that bound, that is not dependent, it's 1 over p. And we just fix some s between r and p, so we just can make this standard. The older estimates that gives you, in the limit, passing them to limit, you get exactly because some constant that goes to 1 because s is arbitrary. And this is the main point, which is quite easy to obtain in this case. After we have this, we go back to the equation for p, take s-test function, fix a w in k1, or I mean, in this, even cannot be in k1 in this space, but which of course contains the L infinity functions with values in k1, and just use this monotonicity argument to get the inequality, okay? And this is basically the idea of Minty. Minty lemma is basically behind this trick. So we get now the main part where we have only the weak convergence of the d into the test function. So we can go to the limit in the inequality. Of course, now integrate also in time. I was using this, which of course, if I integrate in time, is equivalent to, so replace omega by qt, and then I can return, I will explain in a minute, I can return back. But you see, and you can go to the limit, you have everything we need to go to the limit. Each term converges smooth to the corresponding one. But we don't get exactly v here, you get w. So again, the second part of Minty argument is exactly as usual, by a convexity argument, replace this in particular, this holds for all w in this test set, and replacing by this one, since we know already that v verifies the constraint, we can use this for lambda between 0 and 1, and then let lambda go to 0 and you recover v. This is the usual Minty way, Minty argument, so there is no standard technique. And of course, but there is still a difference, we still have integral in time. Now, we must just choose, this is not the kind of Lyon's argument. You just take a w, which is f of t, which is a w only of x in some interval between some instant t0 minus h, t0 minus plus h, and 0 if it's not. And then you see this function, if this w is in k1, this function is in L infinity divided with L1. You introduced here and then you divide by 2h, let h go to 0, and you obtain almost everywhere by Lebesgue's theorem to obtain this. So this is also a known trick. That's it, basically. I mean, you need to see uniqueness, but uniqueness, since you already know that this is bounded by 1, you can apply the difference of the two, Grunwald, and that's it.
Can I ask you a question?
Yeah.
Usually, well, this looks like the Q Laplacian for this.
Yeah, it is. The
So
Q Laplacian,
usually
Q.
for the-
The Q Laplacian.
Well, before you do.
Oh yes, it's PQ. PQ is 2, they are 2
So
Laplacians.
t goes to infinity. I'm used to think of that when t goes to infinity, you get the infinity Laplacian.
Because you don't have the other part. It corresponds to the mu equals 0 case. But here is mu is positive.
Let's say mu is 0. Would you
Yeah.
get?
No, but here I have mu. First, I work with mu positive. And then for this problem, I can let mu go to 0,
And you would get the
Okay.
infinity Laplacian.
which corresponds to Euler.
And also another thing is that they usually divide by p, I guess, one. Call the p, yeah?
No, it's the functional, it's divided by p. You make the functional divided
Oh,
by
you don't have the function, okay, I'm sorry.
No, I have just variational formulation already. Okay? Okay, this is, well, the ideas, the only new idea is the mathematical physical idea of the model, because the rest are basically, well, adapting the techniques to this problem.
So where's the infinite Laplacian if mu is 0, so you get infinite Laplacian?
Yes, in a certain sense, not Laplacian, because it's a system, but the corresponding for this system.
Yeah.
Yeah. Navier-Stokes, infinity Navier-Stokes, whatever you want to call it, doesn't really matter. I don't know what that means for the system, it's much more tricky. Okay.
So you would think mu goes to 0 eventually?
At this stage, yes. I can let's say I make this theorem with mu positive.
Yes.
And then, since I have already this V, which is in this convex set, now I can let, for this problem, let mu go to 0, and I'll obtain the corresponding Euler with this constraint. Existence, not uniqueness. Okay?
So your interest is more in finding a model which is the Q Laplacian inequality. Is that? So it's
No,
variation
there are
of
several
model.
interests here. Okay?
I'm just thinking of the.
I mean, mathematically, there are several mathematical interesting questions. We can return to this at the end. Okay?
Sorry. So if you consider the stationary case and the scalar case, and you have also mu and let the mu go to 0, then
Be
you
careful.
get the plastic torsion?
No. That's more complicated because you cannot do that easily. In general, you cannot do that easily because, it's more delicate. The stationary case is more delicate because even you can always prove the, let's say, for all mu positive, there exists at least a solution. For mu large, there is a unique solution. For mu small, there may be more than one solution, like in Navier-Stokes. Okay? So letting mu to go to 0, now we have a very strong constraint we can do in principle. We can go to the limit. You get variation equality, but
Minimize the Dirichlet energy?
what?
The limit, does it minimize the Dirichlet energy?
No, it disappears. Dirichlet disappears. Is a projection in this convex set of a certain the convection plus the f. Okay, so it's a projection in this convex set in this system. Yeah. So it's not it can be characterized in terms of convex analysis, in terms of Lagrange multipliers, even in a certain sense. But okay, I mean, the abstract theory applies to this type of problems. Okay, the question is, what else can you say more than just what applying the general theorems? Okay. So this completes the first part. Okay, there are some remarks important. Okay, so just two remarks here. In fact, one is that for finite R, you can apply Korn's inequality, which is an ingredient in this. But we cannot apply Korn for infinity because there are counterexamples. It's not true. Okay? And as a consequence, we don't have that the solution is Lipschitz in X. A priori is not Lipschitz in X. Okay? It is in every W1P space, W1R space. So the gradient is order continuous, the solution of the function is order continuous. The gradient, I conjecture up to some set, is also, but it's not yet shown, not yet proved. I mean, the regularity of this problem is not yet set. We can conjecture which regularity we have by similarity with other problems, but it's not yet studied. So it's an interesting mathematical question, I think. It's not trivial. And, the last remark, okay, this is just how to control the convective term, but it's more or less standard. It's just vector algebra. And, okay, this comes now concerning the remark about steady state, you see. The steady state is this problem. It's not difficult to show that for positive mu, you can always have an existence of a solution. The argument is basically for any q, yeah, because you are working in this. So you can also make an approximation with some power. I mean, and as we did for time dependent, it can be repeated. I'm not going into details. It can be also done by a fixed point, like freezing one of those is another way to prove existence. There are several ways to prove existence of this problem. The uniqueness, however, as in Navier-Stokes, by the way, is not true unless viscosity is sufficiently large. So, since we have this constraint, we can let mu go to 0. Yes, you can go mu go to 0 here. But what we get this variation equality, which is nothing else that in the limit, what this corresponds is the projection of this forcing term into this convex set in this space. It exists. It's not unique in general. Factorization of that solution, that's another matter. Okay? I have not studied that, but if you want to look at it, I shall be happy to see the results. Okay, so these are the remarks concerning this first part. But you can go a little further. We can go to consider the same variation equality, basically the same mathematical model, for a space and time variable convex set. So replace now this one by a positive function. Of course, it should be strictly positive, say, strictly positive almost everywhere. And we must have some regularity. It must be Lipschitz in time, because I need control time derivative. And it should be bounded, naturally bounded, otherwise. That would be much more complicated. Probably it can be still solved with just in some appropriate LPs, but that's matter for, I'm not sure if it's, okay, this is for further research. I'm still keeping this bounded gradient case. Sorry, bounded velocity of deformation case. This is not the gradient, this is the symmetric part of the gradient. Okay, the problem is basically the same, but now I change the convex sets, and I can even allow that this convex set depends on time, which turns the problem a little bit more delicate. But basically what we can do is the following. So what is, this is a theorem, yes. So basically we can state an existence and uniqueness as well, if mu is positive, so mu is now positive. Q is any power, and the existence, I mean, the initial condition is still now in the convex set for time 0, must be a compatible condition. This is clear because of the a priori estimate, and the variation equality is the same. Of course, now test functions change every time, almost every time. But basically, the existence and uniqueness theorem for mu positive is the same. But the proof is completely different, as you'll see. Not completely, but it's not just a power. It's more complicated penalization of this coefficient, this viscosity. But, okay, this is just regularity remark. This is just Sobolev embedding. And we can as well consider the time-independent problem, the steady-state case, now making here a C star depending only on X. Okay, and this is only necessary to be bounded in X. No regularity on X is required, more regularity. And the same argument that I spoke before applies. Okay, now, what is the idea? The proof is a little bit more complicated, and goes back, okay, I'll make comments on how these ideas came. But let me explain what is the idea. The idea is to penalize exactly this condition now with psi. And penalize this is in the viscosity coefficient, is a nonlinear penalization, which somehow is more complicated, because this could also can be seen as a penalization of this term. But it's a bit more delicate now, because we have this psi x and t, and somehow this psi must come into the estimates. So I take this kind of function, k epsilon, which approach a maximum monotone graph, as you see. And for large S, I can just truncate somehow in order to work with smoother functions, smoother solutions u epsilon. And for u epsilon, for each epsilon, basically this is a problem which is essentially standard. Of course, I should be careful about the values of Q, but I make Q sufficiently. I can make it. Okay, there a technical issue with Q, but let's not stop on there at the moment. Suppose Q is such that there is a unique, and this is standard to show that this is a uniqueness because this operator S epsilon is still monotone and is still potential. And this is what makes the trick work. Because now I need a priori estimates. And basically, the first one is the same, the energy one, but since you see K epsilon is bounded below by 1, so there's not depend on epsilon. So energy estimate is no problem. The time derivative is a more delicate issue. It works because S epsilon is still potential, and this is the main reason. And of course, the initial data is in convex. So the a priori estimate can be made in this independent of epsilon. But the new estimate now, which replaces the estimate on the P, is the estimate, but only on the coefficient. So the difference now is that we only make an a priori L1 estimate of the viscosity side, not only viscosity, K epsilon. And this is only in L1, which means that we must be careful when now we go to the limit. And of course, I'm not going to in all details, but in any case, we can extract subsequences. We must be careful about the convergence of the convective term, at least in L1. But this is okay now, depending if the Q is small or large. There is this extra regularization if necessary for small Q, but this is a technical issue. So the monotone methods allow to solve the differential inequality, again by a variant of Minty's lemma, provided now we can get the corresponding constraint with psi for this limit, the limit of this subsequence. Okay? And okay, I'm not going to go into much details because we have already enough. But I can. This is just an adapting argument that has been proved in different frameworks, but similar, very similar, for the gradient or for the curl also. It also works in electromagnetism, but it is essentially the same. And in fact, this a priori estimate in the limit can be shown that in the limit, in fact, we have that the positive part, I mean, the measure of the set where this is larger than this in the limit is negligible. So we basically prove that the positive part is integral L1 norm 0. So this means basically that the constraint is almost everywhere satisfied. So this is the new difficulty, the new trick, but it just adapting an argument to this case. What is interesting, and maybe I'll not exhaust my hour, is that, and this is also a way to now to see how this problem, when we have this convex set now depending on this psi, we take two different thresholds psi. Can take two different initial conditions and two different external forces F. And basically we have, for positive mu, you have an existence and uniqueness of solution U1, U2, and you want to estimate the difference. And the difference may be estimated, and this is an interesting conclusion, I think, that gives you an estimate in the energy space. So I just put it here, the case Q equal 2 to simplify. But it's true for, we need to distinguish Q larger than 2, Q smaller than 2, but working with these tricky Q inequalities, and you get similar conclusions, of course. But the conclusion basically is that we can estimate the simple energy of the difference of the two solutions by the L2, I forgot the U0, but you can have U0 here. Take to U0 equal, but or else at L2. Yes, it is L2, the L2 norm of the U01 and U02. I forgot to write it here, but what it is remaining. But what is interesting here is this point. And this is really very important that in fact both are strictly positive. And the L infinity norm is what is really important for the variation of the convex. This remark, in fact, it's not new. It comes from a similar result for the scalar problem that has been considered for the first time by Lisa Sanch. He's my co-worker in a paper in 2002, I think. She made the scalar problem, she got this conclusion. And in particular, we can apply this continuous dependence property for large viscosities, and if we can have a steady state threshold, which is approached with a certain rate when time goes to infinity, we can, with force that goes to zero, we can approach the steady state solution, which in this case, because mu is large enough, is unique, can be approached in L2 by this solution. But is now a little bit more making the standard framework for these variational problems. And this is also true for Q different than 2, but this is a little bit more work. I'm going to skip this today. So just two final remarks before you put your questions as you like. In fact, what is new, made it new here, is the extension to the convective term, to the system with this D constraint. But as I told you, the unidirectional flow reduces the problem to a scalar one, where the convective disappears because they became orthogonal, so disappear. And it's basically a kind of, in P Q equal 2, it's a kind of Laplace heat equation or Q time-dependent parabolic problem with this constraint on the gradient now. In the scalar case, it became the constant on the gradient. And in fact, Lisa Sanch considered this problem in 2002. After we have done a previous variant of this problem for a superconductivity model that was in fact with the Q operator in scalar case and the quasi-variational quality. It was a problem of this type where this psi also depends on u, but u was scalar. So u was scalar in some 1 over q was just a function. And this was the gradient. We have done in a paper that we published in 1999 with the quasi-variational quality, and u was basically a third component of electromagnetic, of the magnetic field in a superconductivity type 2 problem with this kind of constraint. And then Lisa realized that he could apply the flop attack, because in this quasi-variational problem, this was delicate. The time derivative is a measure, it's not in L2. So it's more delicate in this case. But in case that the G is also a function of x and t, the time derivative can be made L2, so the problem becomes variational in classical sense. But in fact, Lisa Sanch has started to work on these problems in her thesis, and she published a paper in Portugal in Mathematics, which is not well known, in the case, scalar case, with constant 1 and time-dependent Dirichlet-Boundary condition. This is interesting because in this parabolic problem with this constraint, even with simple, well, of course it's more complicated if the constraint is depending on time or in x given. But contrary to the elastoplastic elliptic problem, where this is equivalent to a two-obstacle problem by the distance to the minus plus the distance to the boundary, in the time-dependent case, it's not always true. So it's possible to construct counterexample where the constraint on the gradient is not equivalent to the constraint of the two obstacles constructed as the solutions of certain Newton-Jacobi equations related to the constraint. That was Lisa Sanch's work.
Even in elliptic case, that doesn't work always.
Even in elliptic case, if you, yes, that's right, not geometry.
Well,
Depends on the operator. It depends on the operator. Yes.
So connectedness is important there somehow.
What? No, there is in the elliptic case. There are several approaches also. Maybe also in parabolic. I mean, you can also viscosity solutions. You can also use variational solutions, and they are not always equivalent, even for the two optical problems, right? And what we did before, because in fact these techniques that I explain you is an extension to a paper that was published with Fernando Miranda. And in fact, second part of this paper is finished with Miranda and Lisa Sanchez that we published almost 2 years ago, which in fact was also a vector case. And instead of this equation, we have Maxwell equations together with the curl constraint, which is a kind of very corresponding to a special case of superconductivity. So I think what is the challenge here is to see if this variational approach really corresponds or not to this kind of fluid that we have seen in the beginning, but this is not a work for for mathematicians, but for mathematical physicists or rheologists. But is now just one final remark. I have make a first talk here. This talk last September in St. Petersburg in the conference of the 80th birthday of Solonikov, and 2 days later, Harald Gark called my attention that there existed on the web a preprint of similar model, simpler models, just for Stokes, not Navier-Stokes, with numerical approaches, only in this case, without convection. And there are some numerical experiments, but I do not know if these numerical experiments are not validated. And it is a preprint I just met after this, but is independent of this. Okay, thank you very much for your attention.
Yeah, some questions?
Yep.
What is known about the free boundary of such problem?
As far as I know, nothing. Even in the scalar case, parabolic case, I don't know anything about the free boundary. Only in the elliptic case is known.
Even the double obstacle, nothing is known, which is a little bit simpler than this.
I mean, the parabolic double.
Well, even elliptic, the double obstacle.
I don't remember. Are you sure?
Nothing is known.
Nothing is known?
Well, depends. I mean, locally, the two obstacle problem is one obstacle, locally. The only problem is when the two obstacles
Of course,
jump.
yeah, that's exactly.
Okay, so you want to mean when the two obstacles touch, that becomes a Dirichlet problem.
No,
Because-
nothing is known.
You know when they touch,
No, how do you know that?
by definition of the obstacles.
Yeah, but what is the structure of the?
Of course, of this set, which is not clear. It's an assumption, of course. If you have just two general obstacles touching somewhere, you know where they touch. But then if you don't want to make any assumption on that set of contact of the two obstacles, of course, it becomes very, very delicate.
It is very complicated.
Depends.
It is like-
Not necessarily. Suppose that on kind of the assumptions on the contact of the two obstacles. Because after that contact, it's a Dirichlet problem. The question is how the two obstacles detach. Okay? This is what is necessary to analyze. But there are a few things. There are a paper by Moscow in Acta Mathematica about this, but it's for variational solutions, not precise information about free boundary.
Of the solution.
Yes,
right?
only the solution, right,
Not
for the
free
solution.
boundaries, nothing is known.
No, the free boundary does not arrive to free boundary, that's true.
I don't know anything about whether it's a physical problem or not, but it seems to me to be an interesting question about mu equals 0 in the limit problem,
Mm-hmm.
which is whether you have uniqueness.
No uniqueness.
No, I know you haven't got uniqueness at the moment, but the question is whether there is a sensible uniqueness, a uniqueness result without having to go through entropy inequalities or something like this. As a simple model, you might think of the Burger's equation.
Mm-hmm.
So ut plus ux equals 0.
I mean, look at the one-dimensional problem.
Yeah. So with the inequality constraint, mod ux
Mhm.
is less or equal to 1.
Mm-hmm.
So the question might be: do you have shocks? You can't.
No, cannot get shocked
You're not
because
going to get
no,
shocks.
cannot
You
get
don't
because the
shocks.
gradient is
If you don't
bounded.
get shocks, then there's a possibility that you can have uniqueness of the solution without having to go into developing an entropy inequality.
In the
Actually,
time-dependent
that's
problem.
just sorry,
Yeah,
I hadn't
it's-
thought about it. Just a question arose in my head just now.
I do not say there exists, the only thing I said is that I'm not able to show uniqueness. I do not say that there exists multiplicity in the time-dependent case. I do not say that.
No, I'm
It's
just
only in
saying
the steady
this-
state, that is
it would be
clear.
I'm just saying this is an interest. This would be an interesting question. to have
Maybe, I think so,
examples.
yes.
You have the kind of structure. You have the structure of Euler equation, Euler equations.
Mhm.
Where you've got this inequality constraint. If you put f equals 0, the question is about the initial value. The question is about the initial value problem. Is whether it's possible that the variation inequality, the inequality constraint.
The point is this, if you don't have the convective term, the answer is yes.
No, I understand the
But if you have convection, I'm not so sure.
If you take that scale,
Otherwise, you have this point.
if you've got that scale.
Well, in scalar case, it's true.
Yeah, you've got
in
that
scalar
scale,
case-
it's like a tiny dependent sandpile problem.
No, yes, but in scalar case, it's true. The problem is, in the vectorial case, you don't have the Korn L infinity estimate. Okay? Because if you have, so in scalar case, there is no problem, it's true. Grunwald applies in scalar case. But in vector case, you only have the L infinity, the symmetric part of the gradient. So that's more delicate. That's I don't know how to do it. That's why I'm not able to prove uniqueness at this moment.
I'm talking about mu equals 0.
Yes, 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 yes. So the scalar case with mu equals 0, there is uniqueness. Okay?
In the case of the sandpile problem,
Yeah. Yes, that's
I
uniqueness.
was asking the question about the Berg. I'm taking a different type. I'm thinking of Berg. You know, Berger's equation is often a model for Euler. People multiply looking at
Okay.
ut plus ux equals
Okay.
0. blah,
Okay.
blah.
Okay.
Now we consider that. I've been asking this question.
Well, in scalar case, it's my paper with, I spoke in that on Oxford last November. With Lisa Sanch, we already
So you
treated that
consider
case.
this, you consider
In scalar case, we have treated also the quasi-variational problem. First order. And this is, I mean, well,
with the invective.
well, it depends with you here, the uniqueness is more complicated, of course, but without you here, it's okay.
With the invective term.
Yes, yes, yes. If you don't have this, we have treated more general quasi-variational problem. I can give you the reference. It's already published in archives last year. Okay.
Other questions? If not, let's thank our two speakers again.